Before we discuss electrical charge and Coulomb's law, let's review some basics. First, there are two types of electrical charges, positive and negative. Same charges repel, opposite charges attract. Conductors are materials that charges can move freely through. Insulators are materials where the charges cannot move freely. And semiconductors are in between. Also, if we have an electrical apparatus, we ground that. Grounding allows an object to move any excess charges into the earth. And this is important in your home because it helps to prevent you getting electrocuted if there's a short circuit. Instead of the current going through you, it will more easily go to ground. In atoms, you have a nucleus that has protons and neutrons, and around the nucleus you have electrons. A proton has a +1 charge, an electron has a -1 charge, and a neutron has no charge. Now let's look at a conducting solid, say a copper sphere. In such a solid, electrons can move freely. These are the conduction electrons. They can leave behind positive ions. These ions don't move, it is the electrons that move. A charged object can produce an induced charge in another object. So if a negatively charged object comes near a second neutral object, it can repel the conduction electrons away, leaving a positive charge in that area of the second object, which can cause attraction. So if I have a rod that has a bunch of negative charges on it, and I bring it closer to a neutral object, what will happen is it'll repel the electrons away so that the positive charges are left, and this will cause an attraction. On the other hand, if a positively charged object comes near a second neutral object, it can attract the conduction electrons, leaving a negative charge in that area of the second object, causing attraction. So now I have an object with positive charges on it, and we come near a second object. This will attract the conduction electrons, and once again you will get an attraction between these two objects. In both cases, the attraction occurs and the second object maintains a total charge of neutrality. In other words, there's no overall excess charge. The total charge on the second object remains constant. Now let's get to Coulomb's law. Coulomb's law is used for charged particles only, not large bodies. And Coulomb's law determines the electrostatic force between charged particles. So if you have a particle with charge Q1 and a particle with charge Q2, we can determine the force between those charged particles. And that is equal to 1 over 4 pi epsilon sub 0 Q1 Q2 over r squared, where r is the distance between them, which is equal to k times Q1 Q2 over r squared. And notice that k is equal to 1 over 4 pi epsilon 0. So in this equation, r is the distance between the two particles, K is called Coulomb's constant, and that's equal to 8.99 times 10 to the ninth Newton meters squared Coulomb squared, and very often this is rounded to 9.0, and epsilon 0 is the permittivity constant, and that's equal to 8.85 times 10 to the minus 12th Coulomb squared times Newton meter squared, and Q is equal to the charge on each particle, and we'll get to what that actually means a little bit later. The direction of the force is always along the line connecting the two particles. So the force will act along that line, and if Q1 and Q2 have the same charge, in other words, they're both positive or negative, then the force is a repelling force. They move away from each other. And if Q1 and Q2 have opposite charges, then F is an attraction force, an attractive force. They are attracted to each other. Now, what if you have multiple charges? And you want to look at the force on one of the charged particles, let's say Q1. We use the principle of superposition to find that. And in order to get the net force, you add up all the vector forces of each charge that is acting on the particle of interest. So the net force is equal to the force of particle 2 on 1 plus the force of particle 3 on 1 plus the force of particle 4 on 1, etc., up to F of particle n on 1. Now let's discuss shell theories. We'll look at a specific body, namely a shell with charges on the outside of the shell. So the first theory says that if a shell has uniform charges distributed evenly on its surface, a charged particle outside the shell will act as if the shell's charge were concentrated at its center. So the first theorem says that if the charged particle is outside the shell, it acts as if all of the shell's charge is at the center. The second theory says that if a shell has a uniform charge distributed evenly on its surface, a charged particle inside the shell will have no net force acting on it due to the shell's charge. So if a charged particle is inside the shell, we will have no net force on the particle. And that's because all of these forces cancel each other out. And it doesn't matter where you are within the shell, it turns out they cancel each other out in any position. Now let's discuss the fact that charge is quantized. All charges are made up of an elementary charge or a quantized charge, and this is given by the formula Q equals NE, where N is equal to plus or minus 1, plus or minus 2, plus or minus 3, etc. And E is the elementary charge, and that's equal to 1.602 times 10 to the minus 19 coulombs. So, in other words, all charges are an integer multiple of E, because N could be 1, 2, 3, or 4. So, if an atom is a charge of plus 1, plus 2, plus 3, that is the quantized number. Now, don't confuse Q with E. Q is equal to a charge which is plus or minus and always an integer. However, E is the actual number of coulombs, and that is defined as an amp second in a current. So let's do a little bit of an aside for that. Current, which is given as I in amps, is defined as Q over T, where Q is in coulombs and T is in seconds. And basically, it's the rate at which Q charges move past a point per unit time. So this is basically charge per unit time. And so 1 amp is equal to 1 coulomb per second. And we can write this another way, that Q is equal to I times T. And we'll see this later when we talk about currents. But let's get back to our charges. So for a single proton or electron, how many of them would be in 1 coulomb of charge? So the charge on a proton, which is 1, is equal to the charge on an electron, which is also 1, but we're using the absolute value, which is equal to N times E, which in this case is 1 times E, which is equal to 1.602 times 10 to the minus 19th coulombs. So a charge of plus 1 for a proton or minus 1 for an electron will have a plus or minus 1.602 times 10 to minus 19th coulomb. And that's what you use in the Coulomb's law equation. Okay, so if you say that you have an atom with 2 protons, and that's Q1, you don't put 2 in there, you put 2 times E in there to get the coulombs. So again, 1 proton or 1 electron has a charge of 1.602 times 10 to the minus 19th coulombs. On the other hand, how many protons or electrons would it take to get a charge of 1 Coulomb? Well, in this case, we know the charge is 1 Coulomb is equal to n number of protons or electrons times E, which is equal to n times 1.602 times 10 to the minus 19th coulombs. So n would be equal to 1 over 1.602 times 10 to the minus 19th, or that would be equal to 6.02 times 10 to the 18th. That's how many protons or electrons it would take to get a charge of plus or minus 1. Or in other words, 1 Coulomb is the charge carried by 6.02 times 10 to the 18 protons or electrons. So in solving problems, if it states that there are, for example, 3 protons present, we can find Q by using our formula Q equals N times E. So 3 protons would be N, so that's equal to 3 times 1.602 times 10 to the minus 19 coulombs, which is equal to 4.806 times 10 to the minus 19 coulombs. And again, that would be what we put into the formula for Coulomb's law. I also want to point out that charge is conserved. Charge obeys a law of conservation similar to conservation of energy and momentum. Charges can be transferred but cannot be created or destroyed. So, in other words, the total of all the electric charges in a closed system remains constant. The electrons may move around, but the total charges remain the same. Okay, let's get to some problems. The nucleus of an atom has a charge equal to 90 protons. If a proton is fired at the nucleus, what is the repulsive force that occurs when the proton is 1 by 10 to the minus 10th meters from the center of the nucleus? Okay, so we're going to be using Coulomb's law, which is given by this formula. And what we know is that charge is equal to n times the elementary charge. So the charge for a proton, since we have 1 proton being fired at the nucleus, is 1 times E. And the charge of the nucleus is equal to 90 times the proton, so that's 90 times E. So if we plug that in to our equation, we get the force is equal to K, which is 8.99 times 10 to the 9th, times Q1, which we'll call that the nucleus. So that's 90 times E, and E is 1.602 times 10 to the minus 19th, times Q2, which is the proton, which is 1 times E, which is 1.602 times 10 to the minus 19th, over r squared, and we're told that it's 10 to the minus 10th meters. So that would be 10 to the minus 10 squared. And if you go through this math, we get force is equal to 2.1 times 10 to the minus 26 over 10 to the minus 20, or the force is equal to 2.1 times 10 to minus 6 newtons. And I put this problem in to show that when you use the equation in Coulomb's law, you have to convert the charge into coulombs. And you do that using this formula. Here's our next problem. The force of gravity attracts the Earth and the Moon. What amount of equal charge would need to be placed on both bodies such that the force of gravity would be negated? And the mass of the Earth and the Moon is given. So we have our Earth, and we have our Moon, and right now they're being attracted by the force of gravity. And we want to know what charge we need to put on these bodies such that it would repel and cancel the force of gravity. So basically we want the force of gravity to equal the force of the electrostatic repulsion. So force of gravity is G times the mass over r squared equals K times the charge, and it's the same on each body, so that would be Q squared over r squared, which is the same. So we can cancel out the r squared, and we're solving for Q squared. So if we solve for Q squared, that's equal to G, mass of the Earth, mass of the Moon, over K. And we can plug these figures in. So Q squared is equal to G, which is 6.7 times 10 to the minus 11, that's the gravitational constant, times the mass of the Earth, which is 6 times 10 to the 24th, times the mass of the Moon, which is 7.4 times 10 to the 22nd power, over K, which is 8.99 times 10 to the 9th. And if you go through this, you find that Q squared is equal to 0.33 times 10 to the 28th. If we take the square root of that, we get Q is equal to 0.58 times 10 to the 14th coulombs. Or let's just say it's equal to 5.8 times 10 to the 13 coulombs, which is a pretty big charge. So that's what would be needed to negate the force of gravity between the Earth and the Moon. Here's another problem. Three charges of equal value Q are placed at the vertices of an equilateral triangle. Another charge, Q prime, equal to minus Q, is placed at the center of the triangle. In what direction will the charges at the vertices move? So I've diagrammed this for you, and I've shown a few facts from the problem. Our vertices we'll call A, B, and C. We have a charge Q at A, a charge Q at B, a charge Q at C, and they're all equal to +1, which is also equal to the magnitude of charge Q prime, where Q prime is actually -1. So we want to know in this system what will happen to the charges at the vertices A, B, and C. Will they be repelled due to the forces from the charges at the vertices, or will the minus charge Q prime be strong enough to attract them? So let's look at the vertices at C, and we want to look at the force on C from the charges at A and B. So the force at C due to A, that's the nomenclature I'm going to use, is equal to K times Q, which in this case is Q squared, over X squared, because that's how far apart C is from A. We're going to call the length of one side of this triangle X, so that's why we put it in here. And we also have a force on C from B, and that's equal to the same, K times Q squared over X squared. And I've put these forces in over here, and you can see they're acting in a direct line from A and from B. So they're going to produce a force vertically. Now note that if we call this the z direction, the force on C from B, in order to get the force in the z direction, that would be equal to force on C from B times cosine 30 degrees. So our net force on C from A and B is equal to cosine 30 degrees times the force of C on B, which is K, times Q squared over X squared. And we also have the force on the other side, so that we get 2 times that. Now we want to know what the force is on C due to Q prime, which is in the middle of the triangle. So that's equal to K times Q prime times Q over Z squared. And we're going to call the distance from C Z. That's the distance. Well, how does Z relate to X, the side of the triangle? Well, that distance Z is equal to 1/2 X times the cosine of 30 degrees. Because if you bring this down, this total distance is equal to X times the cosine of 30, and we want half of that. So that's equal to 1/2 X times the cosine of 30. So that's equal to 1/2 X times 0.87, or 0.44 X. So now we know how Z relates to X. And in this equation, we're using Z squared, so Z squared is equal to 0.19 X squared. So we can substitute that in, and we get the force on C from Q prime is equal to K. And since Q prime and Q are of equal magnitudes, we can call that Q squared over 0.19 X squared, which would be that Z squared, which is equal to 5.3 K Q squared over X squared. So let's summarize this a bit. We have a force on the charge at C from the charge at A and B, and we found that that total force is equal to that amount. So the force on C from A and B is equal to 1.7 K Q squared over X squared. And we just found that the force on C due to the Q prime charge, which is a negative force, is equal to 5.3 times K Q squared over X squared. So as you can see, this force is greater than that force. The attractive force of Q prime is greater than the repulsive force from the charges at the vertices. So that would mean that the charges at the vertices would move in towards the center, towards Q prime. In other words, these charges would all move in towards Q prime due to a greater attractive force of Q prime than the repulsive forces of the Q's at the vertices. Let's do one more problem. Two balls, both with mass of 0.2 grams and charge Q, are suspended from strings. The strings end up at an angle of 70 degrees from each other, and the balls end up 50 centimeters apart. What is the charge on each of the balls? So I've diagrammed this. You can see the two balls hanging, and they have a charge Q, which we're trying to find. And since they are stationary, they're in equilibrium, and we know then that in equilibrium, the sum of the forces in the x direction has to equal 0, as do the sum of the forces in the y direction. So if we look at these two components, so let's look at our x direction first. And our forces are the electrostatic force that's pushing the balls away has to equal the force of tension in the x direction, which is up here. And the force of tension in the x direction would be the total tension times the sine of 35 degrees, or our electrostatic force is equal to 0.57 times T. Now let's look at the forces in the y direction. Well, we have our force due to gravity, which is mg, and that has to equal our tension in the y direction, which is here, and that's equal to tension times cosine of 35 degrees. And if we put in the numbers, the mass, which is 0.2 times 10 to the minus 3 kilograms, times g, the gravitational acceleration, which is 9.8, has to equal 0.82 times t. Or we get t is equal to 2.4 times 10 to the minus 3 newtons. Now, if we call this equation 1, we can put the value for t into equation 1, and we get that the electrostatic force is therefore equal to 0.57 times t, which is equal to 0.57 times 2.4 times 10 to the minus 3 newtons. And if we do the math, we get our electrostatic force is equal to 1.37 times 10 to the minus 3 newtons. But we also know that based on Coulomb's law, the electrostatic force is equal to K times Q squared over R squared, which is equal to 8.99 times 10 to the ninth times Q squared over 0.5 meters squared. And we found what the electrostatic force was. That's 1.37 times 10 to the minus 3. If we then solve for Q squared, we get Q squared is equal to 3.8 times 10 to the minus 14th coulombs, or Q is equal to 1.95 times 10 to the minus 7 coulombs, Or we could say that Q is equal to 0.2 times 10 to the minus 6 coulombs, or 0.2 microcoulombs. And that is our answer.